What is the world made of? This simple question has ignited one of the most dramatic and consequential quests in human history. In this episode of the Human Odyssey, we journey back to the clandestine laboratories of the alchemists who chased dreams of eternal life and limitless wealth. We witness the birth of the scientific method as brilliant minds began to dismantle ancient myths with radical experiments. We feel the thrill of discovery as the fundamental elements of our universe are identified one by one, like finding the alphabet to a cosmic language. The story culminates in a moment of breathtaking genius, the creation of the periodic table, a map to the very building blocks of reality. But the journey doesn't end there. We then plunge into the invisible world of atoms and molecules, learning how these tiny particles combine to create everything from the water in our oceans to the complex machinery of our own bodies. This is not just a story about science, my friends. It's a story about human curiosity, our relentless drive to solve the ultimate puzzle of our existence. This is the Human Odyssey, and today we'll be talking about the story of chemistry. The air in the room was thick, a potent cocktail of sulfur, secrets, and smoldering charcoal. It clung to the heavy velvet curtains and settled in the lungs like a fine, gritty dust. This was the scent of creation, or at least a desperate, feverish attempt at it. In the heart of this dimly lit chamber, a man we might call the Seeker hunched over a bubbling alembic, his face illuminated by the flickering orange glow of the Athener, the long-burning furnace that was the heart of his laboratory. He was an alchemist, a chaser of whispers and ancient texts, a practitioner of the ars magna, the great art. To a modern eye, he was a mystic, a charlatan, a fool. But to himself, and to the lineage of thinkers stretching back through the sands of Egypt, Persia, and Greece, he was a philosopher of matter, a sacred detective on the trail of God's own blueprint. His quest was twofold: a pair of ambitions so grand they bordered on madness, to concoct the elixir of life, a potion that would grant immortality, and to discover the Philosopher's Stone, a mythical substance capable of transmuting base metals like lead into pure, shimmering gold. For the Seeker, lead and gold were not just different metals, they were different states of being. Lead was sick, corrupted, and imperfect. Gold was pure, divine, and eternal. He believed all matter was a single primordial substance, the prima materia, just wearing different masks. The universe, he thought, was a place of becoming. A seed becomes a tree, a caterpillar a butterfly. Why then could lead not become gold? All it needed was the right encouragement, the right medicine. The Philosopher's Stone was that medicine. His laboratory was a universe in miniature. Glass vessels with serpentine necks, retorts, cucurbits, and pelicans stood like strange glass creatures. Charts of the heavens papered the walls, for he believed the cosmos was intimately connected to the crucible. The 7 known metals corresponded to the 7 celestial bodies. Gold was the sun, silver the moon, iron was Mars, and lead, heavy and dull, was Saturn. To perform an operation on a metal was to engage in a celestial dance. He worked by a code of symbols and allegories. He didn't write mix sulfuric acid and saltpeter. He wrote, "The green lion devours the sun." It was a language designed to protect his secrets from the unworthy and perhaps to elevate his work from mere craft to a spiritual rite. He would heat, cool, dissolve, and distill again and again in a cycle of operations he called solvit coagula, dissolve and coagulate. He was trying to break matter down to its essence and build it back into a more perfect form. He failed. Of course he failed. He never turned lead into gold. He never brewed a drink for eternal youth. For centuries, seekers like him across the world toiled in their smoky labs and died, their dreams turning to ash alongside their charcoal. From our perch in the future, it's easy to dismiss him, but to do so is to miss the point. The alchemists, in their magnificent, misguided quest, were asking the right question. What is stuff? And in their relentless pursuit, they weren't just mixing potions. They were inventing the tools and techniques that would one day unlock the very secrets they sought. They perfected distillation, discovered new acids and compounds, and meticulously documented the strange transformations they witnessed in their flasks. They were the dreamers, and every great journey begins with a dream. They laid the foundation, a chaotic, mystical, and utterly essential bedrock of curiosity upon which the cathedral of modern chemistry would be built. Centuries passed. The world was changing. A new light was beginning to filter through the dusty windows of the old ways of thinking. A light called the Renaissance. And then the Enlightenment. It was a light that valued observation over allegory, evidence over ancient authority. Our seeker, no longer a single man, but the spirit of human inquiry itself, found himself in a different kind of laboratory. The air was cleaner. The astrological charts were gone, replaced by meticulously kept notebooks. This was the age of Robert Boyle, an Irish aristocrat in the 17th century who is often called the first modern chemist. Boyle was a man caught between two worlds. He was fascinated by the alchemist's quest and spent a great deal of his life trying to achieve transmutation. But he was also a pioneer of the new scientific method. He was a skeptic. He wasn't satisfied with the green lion devouring the sun. He wanted to know what was actually happening in the flask. He took aim at the ancient Greek idea, cherished by the alchemists, that everything was made of four elements: earth, water, air, and fire. It was a beautifully simple idea. It felt right. But was it true? Boyle looked at a piece of wood. When you burn it, you see flames, fire. You see smoke rising, air. You feel moisture, water. And you are left with ash, earth. It seemed to work. But Boyle pushed further. He performed an experiment. He took a metal, weighed it precisely, and then heated it in a crucible. The metal transformed into a powdery substance, a calx. The alchemists would say he had driven out some of its essence. But Boyle did something revolutionary. He weighed the calx. It was heavier. This was a profound paradox. If heating the metal drove something out of it, how could it end up weighing more? It was a crack in the foundation of a 2,000-year-old idea. Boyle didn't have the answer, but he had a better question. And he proposed a new definition of an element. A substance that could not be broken down into simpler substances by chemical means. It was a simple, practical, and devastatingly powerful idea. The search was no longer for a mystical prima materia, but for these fundamental, unbreakable building blocks. The hunt for the elements was on. The spirit of the seeker was now a whirlwind of excitement. The mystery was deepening, the clues becoming more tangible. But a ghost still haunted the laboratory. It was a ghost called phlogiston. Imagine fire. What is it? For the better part of a century, the leading minds of Europe had an answer. When something burns, they said, it releases a substance into the air. This substance was invisible, weightless, and present in all flammable materials. They called it phlogiston, from the Greek word for to set on fire. The theory was incredibly elegant. Wood was rich in phlogiston. When you burned it, the phlogiston flowed out, leaving behind ash. A metal, when heated, became a calx because it lost its phlogiston. It explained combustion, rusting, and even breathing, which was seen as a kind of slow internal combustion. But Boyle's paradox remained. If a metal lost phlogiston to become a calx, why did the calx weigh more? The phlogistonists came up with a clever, if slightly desperate answer. Phlogiston had negative weight. it was lighter than nothing. It was a brilliant patch on a leaking theory. But the leak was getting bigger. The stage was set for a revolution, and the man who would lead it was a French aristocrat with an obsession for precision and a flair for the dramatic. Antoine Lavoisier. And now let's step into the laboratory of Antoine Lavoisier in 18th century Paris. It is a spectacle. It is the finest scientific facility in the world, filled with custom-made instruments of breathtaking precision, balances that could measure the weight of a fingerprint, gasometers to capture and quantify the invisible, and enormous lenses to focus the sun's rays into a beam of intense heat. Lavoisier was a tax collector by trade, a position that gave him the wealth to fund his scientific passions and ultimately would lead him to the guillotine. But in the 1770s and 80s, he was the king of chemistry, and he was determined to slay the ghost of phlogiston. He repeated Boyle's experiment, but with a crucial addition. He heated a piece of tin in a sealed glass retort. As before, the tin turned into a white calx. But Lavoisier noted two things. First, the total weight of the sealed retort, glass, tin, and the air inside, had not changed one bit. This was his foundational principle, the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. It just changes its costume. Second, when he broke the seal, he heard a rush of air into the flask. This was the eureka moment. Something from the air inside the flask had been consumed in the reaction. And when he weighed the calx, it was indeed heavier than the original tin. The extra weight hadn't come from nowhere. It had come from the air. Lavoisier had discovered that air was not a single element. It was a mixture. And one part of it, which he would eventually name oxygen, was the active ingredient in combustion. When something burns, it doesn't release phlogiston. It rapidly combines with oxygen. When a metal rusts, it slowly combines with oxygen. The calx was heavier because it was the metal plus the weight of the oxygen it had taken from the air. He had killed phlogiston. He had redefined the elements. He had established the importance of quantitative measurement. He wrote the first modern chemistry textbook, and in it, he listed all the substances he believed to be elements, including things like gold, iron, and sulfur, and also light and heat, which he called caloric. He wasn't perfect, but he had transformed chemistry from a collection of recipes and mythical ideas into a rigorous quantitative science. The seeker, the spirit of inquiry, now had a grammar for the language of matter. The age of chemistry had truly begun. With Lavoisier's framework in place, the 19th century became a gold rush for elements. Chemists across Europe were isolating new substances, each one a fundamental character in the story of the universe. There was sodium, a metal so reactive it bursts into flame on contact with water. There was chlorine, a pale green poisonous gas. There was iodine, a solid that transformed into a stunning violet vapor when heated. The list grew longer and longer, and by the 1860s, there were over 60 known elements. And to our seeker, it was starting to feel chaotic again. It was like having a jumble of letters from an unknown alphabet. There was no order, no sense. Were these elements just a random collection of cosmic accidents? Or was there a hidden pattern, a deeper logic waiting to be discovered? Many tried to find it. They arranged the elements by atomic weight, a concept pioneered by John Dalton, who had resurrected the ancient Greek idea of atoms, tiny, indivisible particles of matter. They noticed that certain elements behaved similarly. Sodium was like potassium. Chlorine was like bromine and iodine. These are families of elements. It was tantalizing. It felt like being on the edge of a great revelation. The man who would have that revelation was not in a fancy lab in Paris or London. He was in the sprawling, wide-swept expanse of Russia, and his name was Dmitri Mendeleev. Mendeleev was a man of wild hair, a fiery temperament, and a passionate belief in the underlying order of the universe. He was a professor at the University of St. Petersburg, and he was writing a chemistry textbook. He wanted to find a logical way to present the elements to his students. The story, perhaps apocryphal but too good not to tell, is that he was obsessed with the problem. He wrote the name of each element, its atomic weight, and its known properties on a separate card. He laid them out on his desk like a game of chemical solitaire, shuffling them, arranging them, searching for the pattern. He played for days, fueled by tea and obsession, until he fell into an exhausted sleep. And in a dream, he saw it. He saw the table, complete and whole, where all the elements fell into place as required. When he woke, he immediately drew it out. Of course, remember, I said that at the beginning, the story mostly apocryphal or not true. But too good not to tell, right? But anyway, what Mendeleev did was an act of pure genius. He arranged the elements in rows by increasing atomic weight, but when he came to an element that behaved like one in a previous row, he started a new row, placing the similar elements in the same column. This created a grid, a table. But here's what made this table revolutionary. To make the pattern work, he had to do two audacious things. First, he had to leave gaps. He predicted that there were elements that had not yet been discovered, and his table told him exactly where they should be. He even predicted their properties with stunning accuracy. He called one Eka aluminum, meaning one after aluminum. A few years later, a French chemist discovered an element he named gallium. Its properties, its density, its melting point were a near perfect match for Mendeleev's prediction. The gaps in his table were not failures. They were prophecies. The second, he had to occasionally break his own rule. To keep elements in the right families, he sometimes had to place a slightly heavier element before a lighter one. He trusted the family resemblance more than the measured weight. He was betting that the chemical properties were the true guide, and that perhaps the atomic weights were measured incorrectly. He was right. We now know that the true organizing principle is the atomic number, which is the number of protons in an atom's nucleus, not the atomic weight. But Mendeleev's chemical intuition had led him to the correct arrangement anyway. This was it, the periodic table. It was more than a chart. It was a map of the universe's Lego set. It was a cosmic Rosetta Stone. It showed that the elements were not a random jumble, but a family with deep, ordered relationships. It was a single, elegant, and beautiful piece of scientific art that revealed a profound truth about the nature of reality. The seeker, who had started in the smoky den of the alchemist, now stood before this table, and for the first time, the language of matter made perfect, harmonious sense. The quest to understand what things were made of had reached its climax. The periodic table was the cast of characters. Now the seeker had to understand the plot. How did these elements, these atoms, interact with each other to create the infinite variety of the world? The water, the rocks, the air, the flesh and blood of life itself. The story now moved from the elemental to the molecular. Imagine two hydrogen atoms floating in space. Each is a tiny nucleus with a single electron orbiting it, like a lonely moon around a tiny planet. As they drift closer, they begin to feel an attraction. The nucleus of one atom starts to pull on the electron of the other. There is a point of perfect balance where they are close enough to share their two electrons, which now dance around both nuclei, binding them together in an intimate partnership. They have formed a molecular of hydrogen H2. This sharing of electrons is a chemical bond, the fundamental glue of our world. Now imagine an oxygen atom. It's bigger, more powerful. It has 6 electrons in its outer shell, but it desperately wants 8, the magic number for stability. It's a powerful electron bully. When two hydrogen atoms wander by, the oxygen atom makes them an offer they can't refuse. It shares its electrons with them, and they share their electrons with it. The result is a single stable molecule, H2O, water. This is the drama of chemistry. It's a story of atoms wanting, taking, and sharing electrons to achieve stability. Some, like sodium, are generous, happily giving away their single outer electron. Others, like chlorine, are greedy, desperate to grab one more electron to complete their set. When sodium meets chlorine, it's a chemical love story, or perhaps a robbery. Sodium gives its electron to chlorine. The sodium, having lost a negatively charged electron, becomes positively charged. The chlorine, having gained an electron, becomes negatively charged. Opposites attract, and they stick together like tiny magnets, forming sodium chloride. Table salt. This dance, this atomic ballet, is happening everywhere all the time. Carbon, the ultimate connector, can form 4 bonds, allowing it to build the long chains and complex rings that form the backbone of life. It links up with hydrogen, oxygen, nitrogen, and a few other key players to create the vast and intricate molecules of biology. The sugars that gave us energy, the fats that store it, the proteins that act as the microscopic machines in our cells, and the most famous molecule of all, deoxyribonucleic acid, or DNA. The seeker, who once tried to brew an elixir of life from herbs and metals, now saw that the secret of life was not in a magical potion, but in the elegant, precise, and mind-bogglingly complex arrangement of these very same elements Mendeleev had put on his table. The structure of the DNA double helix, 2 long strands of atoms twisted together, holds the code, the blueprint, for building a living thing. It's a molecule that carries information, a chemical sentence written in an alphabet of 4 repeating units. The quest that began with a desire to perfect matter had led to the understanding that matter had already achieved a kind of perfection on its own. It had organized itself through the simple laws of atomic attraction and bonding into systems capable of replicating, evolving, and even contemplating their own existence. And my friends, the journey of our seeker is not over. It will never be over. The story of chemistry is still being written. Today, chemists are designing new molecules to fight disease, creating new materials to build a more sustainable world, and peering into the fleeting femtosecond-long moments when chemical bonds break and form. The quest that started in a dark, mystical room has led us into the light. We have traded the philosopher's stone for something far more valuable: understanding. We may never turn lead into gold, but we can do something far more magical. We can understand why lead is lead and gold is gold. We can look at a glass of water and see the silent, eternal dance of oxygen and hydrogen. We can look at our own hand and marvel at the fact that it is a temporary, self-organizing collection of stardust, a complex chemical reaction that has been running for a few decades and has somehow produced the astonishing gift of consciousness. The alchemist's dream was not entirely wrong. There is a kind of transmutation at the heart of the universe. It's the transmutation of simple atoms forged in the heart of dying stars into the stuff of planets, oceans, and life. The great art is not about forcing matter to bend to our will, but about understanding its own inherent, breathtaking creativity. The seeker's journey continues, not in a search for a magical stone, but in the endless, unfolding story of the atoms and their dance. The story of us. And with that, my friends, we come to the end of our episode for today. Another episode from our series, The Human Odyssey, and today we were talking about the story of chemistry. I hope you enjoyed the story. I hope you learned a thing or two. And remember, if you want to have access to all our episodes, you can do that by becoming a subscriber on Apple Podcasts or Patreon. I'm Danny, and this is English Plus Podcast. Remember, never stop learning. I will see you again next time.